Hello, welcome back. My name is Mr. Steele, and I'm here to work through another video in the series supporting you in your work with the Honors Pre-Calculus ESQ model for quarter 1 or quarter 2, or possibly quarter 3 if you're an accelerated. In this video, I'm going to give you some background information about the topic in question, which in this video's case is transformations, basically graphing functions from common families and then moving them around the coordinate plane. In this video, as I said, I'll start with a brief overview, then I'll do each of the two problems thoroughly and carefully, talking through every step and every piece of the process that I'm using. Then finally, I'll do a quick little wrap up before we call it a day. It's the same process I've used for videos 1 and 2 in this series, and I'm planning to do for the remaining 7 videos after this one. 7 because 10, 11, and 12 are combined together. So with that said, let's dive into transformations and get you, let's make it so you can transform your knowledge of transformations. So to kick things off, there are 3 little ideas, not little ideas, I'd say these are even big ideas that I want to get into your mind before we start, at least if you're looking for more than just kind of someone to go through a specific problem. And those 3 ideas are the 3 listed here. And I guess I called them key ideas as opposed to like big ideas, but these are all 3 important concepts that you'll need in order to attack these problems and to effectively use transformations when you're graphing functions or writing their equations, analyzing them, any of those key mathematical skills we do with graphs. So the first one is simply the idea of parent graphs. And really a parent graph is just sort of a simplest version of the function. It usually is centered in the origin in some way. It usually grows at a particular rate of 1. It's hard to define some of these things without calculus. So let me just point out parent graphs are the most basic version. They're sort of the unit version, sometimes you'll hear that language, for each of the major graphical relationships that you know. So the parent graphs themselves, the ones that we run into, as far as I can tell, in this course and in the ESQ for Honors Pre-Calculus, include the quadratic equation, y equals x squared, the cubic equation, y equals x cubed, and these 2 are sort of representative of all higher degreed. So basically they sort of represent x to the odd and x to the even as long as those numbers are larger than 1. In addition to those, you'll have their inverses, y equals the square root of x, although it's not quite a full inverse, you get the idea, as well as y equals the cube root of x. And I'll give you shapes in just a second. In addition, as I believe we see here, we have the absolute value of x, so the positive maker. We also should have, if memory serves, I'm trying to recall if they include this one in here. I think that they do, y equals 1 over x. So those are the ones that are there. And you know what, let's throw one more out there just because I think there's a good chance it shows up. Y equals b to the x. And I think they usually use 2 to the x, so let's put that in there as the function. We'll set logs aside. I think that's kept separate. So with each of these are called the parent graphs because they are sort of the foundational relationships. They're the ones that we're going to run into here as you go to sketch these relationships and transform them into new versions. So as far as their shapes, just to kind of get you a general idea, y equals x squared is your classic parabola. The parent itself opens upward. You've done plenty with quadratics and parabolas, so I'm not going to go into too much depth. Likewise, you probably know what we at Franklin know as sort of the first noodle, like Captain America was the first Avenger. X cubed is the first noodle. It basically flattens in the middle, but otherwise behaves sort of like a line. It's just curving as it goes. It grows much faster than x does. Next we have the square root. As I mentioned earlier, I said it was the inverse of x squared, but they can be a little more specific than that. It's the positive inverse side of the inverse. So we get that piece. It starts at a vertex. We'll talk about that point that I just labeled on there later. In fact, I should probably be drawing little points on here as I go. And then there's the inverse of the cubic, which is literally just that same exact shape, but sort of sideways. So it's like a sideways noodle. After that, we got the absolute value, which I'm absolutely sure is going to show up here. That's basically a single line, but never negative. So the negative part flips upward. You get that V shape that we know and love. We have what I call a flying squirrel, but it's actually technically called a hyperbola, and that is defined by 2 branches of the hyperbola and then a vertical asymptote. And in most cases, you'll have, in pretty much every case for what you would potentially graph here, you'll also have a horizontal asymptote. So you'll have a VA and an HA, vertical asymptote and horizontal asymptote. And then last but not least, for the ones that are reasonable for the basic standard quiz here, you could have the typical exponential function, which has only a horizontal asymptote. It starts really small and then grows really big and fast. So those are essentially the 7 that I would expect to potentially show up here. You also graph polynomials in other sections on this ESQ, so there might not be too many x squared and x cubed, but they fit into the work that you're going to do here, so I think you might actually run into them. The second piece I wanted to address is the transformation family. Basically, for this ESQ, there are particular transformations that you're going to be presented with that you'll have to then recognize and then translate into equation form from a given graph. So as far as what the transformations are that are relevant here, and again, that's here, like there are other ones like a scalar adjustment that can actually show up, just not on this ESQ from what I'm told. So the ones that you're on the lookout for are going to be first and foremost what we call a horizontal shift, and I'm going to abbreviate them just for simplicity. The second one, of course, would be the corresponding version, but going up and down. That would be a vertical shift. So horizontal and vertical shifts are possible. Now, how do they show up in an equation? Well, in a horizontal shift, you'll have something changing on the inside. You'll have x minus h in there, where h is some non-zero number. That's going to shift it h units to the right. Obviously, if it was x plus h, that would shift it h units to the left, because it'd be negative h units to the right. Likewise, for a vertical shift, it's very similar, but in this case, you'd have the function plus some constant k. So those two show up all the time. In fact, I think of the examples that are over there, one of them may have both a horizontal and a vertical shift. In addition to that, as I said, there are only certain ones that are going to show up for us here. The only other one that we're going to run into is going to be a vertical reflection. The vert refl. Okay, I'm probably abbreviating too much, but so it goes. What that's going to look like is just having a negative sign out in front. And again, this isn't all of them. There are many others that are out there, including what is there? There's a horizontal reflection, there's scales and dilations, but these are the 3 that you're going to be looking at. You're going to have to recognize these in the function you're provided, as well as the parent graph, and then go backwards and actually determine its equation. So there are the 3 to be on the lookout for. And then finally, last but not least, we're going to be looking for a locator point. The best way to describe a locator point is just that I've sort of marked them already up here. I'll just put them in pink up at the top again. It's an important spot. It's sort of a place of symmetry. It's a place of beginnings, of an origin of sorts. The only exception is this one over x, where the origin point, or the locator point, isn't actually a point on the graph. It's just sort of around. But basically, they're a point that provides definition and gives us a little bit of context for where to kick things off. The important thing for you to know, though, is that if you have a transformed function, which I'm going to write as a times f of x minus h plus k, and I guess that technically I shouldn't have an a here, but we'll let it go. That's going to give us a locator point of h comma k. So it's basically the combination of your horizontal shift and your vertical shift. That tells you where your locator point's going to be in pretty much every single case. So that's what we're looking for when we talk locator point. And of course, as I said, some of them aren't truly points. That would be true for 1 over x. And with 2 to the x, there's a little bit of a wrinkle up there, but this is going to guide you pretty true from there. So here we are. And with that said, we can go ahead and kick things off by doing our first of 2 problems, if not just doing the second of those 2 problems. So in question 3, you're asked to write the equation of the function graphed as well as to find its range. So in this case, we're asked for range. On the second one, maybe it'll be domain. We'll have to see. The one nice thing, though, is that we're told to assume that a is plus or minus 1, and that's really helpful because it just means that there's not going to be any scaling or dilation that happened to our graph. We're just going to have to figure out whether it's positive or negative. So as far as an approach goes for a question like this, I think the best place to begin, and this isn't really like, sort of like the key idea or anything that we need to put in our strategy, but I think this is a good approach to take as you go in. The first thing is to figure out which parent graph are we looking at? Like what type of function is it that we're dealing with here? So by making that determination, looking at the big structure, we can get into this problem really quickly. So as I look at this one off to the side, I see that familiar shape. It looks like half of a parabola, but specifically a sideways parabola. That shape corresponds to the square root of x. So we have an even radical. We're going to assume it's a square root. Like, of course, it could be a 14th root or a 586th root. We don't know. We're just going to go with what we have. So basically, we'll play it safe that way. Cool stuff. So there's our first bit. The second thing we need to do is to figure out where the locator point is. Basically, where are things beginning? Where is that central point? Because that locator point is going to cue us in, or clue us in, I guess we could say clue us in, to the form that our equation is going to take. It's going to tell us what h and k are for the horizontal and vertical shifts. So for us, with a radical, our locator point happens right here at the vertex, or where the vertex would be. So our locator point is going to be exactly there. In this particular case then, the locator point appears to be the y-intercept 0, 3. Notice that that has x-coordinate 0 and y-coordinate 3. So we have our locator point, we have our parent graph. With those in place, we can then bring it all together by putting this into our equation. So basically our equation is going to fit that form, a f of x minus h plus k. If you need to do that, if you need to kind of put it into one of those forms, you can. And I will note, by the way, that it says to write this as an equation, so I'm just going to call it y just for simplicity, but you can kind of choose your own adventure when you get to that spot. So for now, what do we look at? Well, we got the parent graph and the locator point taken care of. We can also tell that this is going to be a positive square root. I didn't mention that before, but this one is opening upward. So technically it's opening downward. It's curving upward, so this is the positive half. So basically we're going to have just positive 1 in front, so I'm not going to write it. Instead, I'll just leave it as the square root of x minus 0, and then plus our vertical shift of 3, which of course we can simplify into being y equals the square root of x plus 3. So there is our part A answer. There's our equation for this graphed function, or this transformed parent graph if you prefer. As for the second bit, where it actually asks us to find its range, well, in this case, we've got to look at our function and figure out what y values does it attain. So in order to determine the range of a function, we need to figure out the specific y values, like what y's show up on here. And to do that, there's lots of different approaches. I think this one's pretty straightforward. I used to use like this beep test thing that I found online on a blog in like the late 2000s. But you could look at this instead as just kind of figuring out where do we begin. So I see that we're starting here. And then basically our graph is getting bigger from there. And since there is this arrow, that means to assume it continues onward forever. There's no other indication that it's going to stop anywhere or it's going to approach any number. So this is telling me it's going up as far as we can get. So for me, this looks like this equation is going to, or this function is going to progress towards y equals infinity, or progress to infinity, meaning grow without bound, but that it's beginning right here at y equals 3. And since we have a closed dot, that tells me we're going to include that value as well. So for range, I would say that this is going to be y as a member of, and then we would include that first y value, which was 3, and then progress on to infinity. Now, if you prefer to use inequality notation, you could also say that y is greater than or equal to 3. It's sort of up to you how you want to approach it. And then there's always the possibility you could use a fancier version of the notation and say it's the set of all y such that y is an element of 3, infinity. I would argue that that last one is overkill. I wouldn't go that way. I'd say that you're probably looking at this as your answer. I think that's where most people will land. But of course, this would be valid as well. Both of those are really good answers. Totally fine down here again, but just a little bit fancier for what we're looking for. So there is our piece. Remember, there are only two things we are looking for, our equation and our range. And obviously, it won't take you that long as you dive in, but this gives you a good sense of sort of what my process is, what my sequence of thinking is as I approach one of these questions. That's going to bring us to our second and final question for this particular problem on your ESQ model, and that is a function that looks like an upside down V, like someone started drawing a triangle and then just went, nah, I don't feel like finishing it. However you want to see it, there we go. The top of a pyramid, lots of options. So once again, our job is to write the equation of the function that's graphed, as well as to find its range, keeping that assumption about a, the leading coefficient, being plus or minus 1, so that way we don't have to worry about any sort of scaling or dilation. So from here, I'm going to follow the same process as in number 1 on this section. So if you're really confused or you feel like I go faster than you'd like, I'd encourage you to look back at question number 1 or I, where I go through things a little bit more carefully and methodically. In this case, we're going to dive in, though, right off the bat. I think we're good to do that here. So first of all, parent graph. That's all about shape. Like, what shape are we seeing? Well, I noticed that there's a V, and while that does make me think about the Mighty Ducks, and D2, the Mighty Ducks, and D3, the Mighty Ducks, a series of movies about not ducks, but hockey players. Basically, when I see that V, I think of the absolute value. This looks like the absolute value of x. In fact, we should expect it to be that without any other information. So we've got an absolute value function, and to find our locator point, we just look for the vertex. So our vertex in this case occurs right there. That appears to be the ordered pair -2, nope, just kidding, kind of in the wrong direction. -1, -2. So there we go. We've got our point. There's our x coordinate and y coordinate locator point, which is telling us our h and k for the equation. And that is where we're going to wrap things up here. We're going to write into our equation. So when you go to write it in there, you might be able to quickly combine the information. So we're going to have the absolute value, and it was absolute value of x, but we do have that locator point, like x coordinate at -1. So that's going to give us the absolute value of x plus 1, so that way -1 zeroes it out. You can think of that, by the way, as x minus a -1 if you need to. And then we're subtracting 2, or shifting down 2, so we'll also subtract 2. Now before you jump in though and go, cool, we got it, we're done, there's actually one thing left. And that is our parent graph opens upward. It's like a volcano that's been flipped on its head. Well, this one's pure volcano. It's basically like pointing upward. So in this case, our graph has been reflected vertically. So because of that, we need a minus sign. So there is the equation that you see graphed at left, based on what we're seeing at the very least. So there's our the equation of the function. And by the way, just like I said last time, it is asking for an equation. So you should say y equals, or g of x equals, or f of x equals, something so that the way there is an equation between two variables, or two things. Now that was the first bit. We do also have to find its range, just like we did last time. And I want to sing something like, home, home on the range, where the deer and the antelope play. It's been a while. I'm born in Arkansas, so got some of that natural accent. But in any event, to find that, we're looking for y coordinates. So just like last time, we're trying to figure out what y values does this graph attain over the course of its existence, or its domain. So to do that, I'm looking at y's. I'm seeing everything sort of begins here, and then it proceeds downward. And as I mentioned in problem number 1, basically those arrows indicate that it's going to go on forever in that direction. There's not going to be some sudden change that suddenly interrupts things. There's no rug pulling out from under you going, ha, you thought it was going to continue. Well, joke's on you. At -160, it changes. There's nothing here. It's just going to continue following that same pattern. So based on that, it's looking to me like we begin at y equals -2 and then proceed downward to -infinity. So if you wanted to use interval notation, you could say y is an element of -infinity to -2, and because that is a closed dot there at the vertex, we include -2. On the other hand, if you prefer not to use this interval notation, although I think most of you will probably use interval notation, you could write this as a straight inequality. You could just say that y is less than or equal to -2. That is also a correct way to do it. And finally, just because it's possible, you might really like, I think it's called set builder notation. There is another way you could say it. You could say it's the set of all y's, such that y is an element of -infinity to -2, including -2. So that is correct as well. I don't think anyone's going to go that route, but like I said, I'm trying to give you a complete coverage of this topic, not a partial one. Like, I'm trying to transform your understanding, not let it stagnate. And so, with that said, that's going to conclude our video. So just as kind of a quick little overview to recall you back, we started by talking about the parent graphs that are out there, the ones that you can expect at least to show up potentially on the ESQ. We talked about the specific transformation families that show up on the ESQ. There's only 3 from what I've been told. Those are horizontal and vertical shifts and a vertical reflection, or what most people know as kind of the flip. And then lastly, we talked a little bit about locator points, which are, well, for the most part, except for with the rationals, they're points that help you locate the graph's placement in the grid. So, pretty self-explanatory. From there, we went and did our 2 examples. One was a positive radical, the other was a negative absolute value. But I would like to say that we had a very positive experience overall. So, with that said, I'm going to stop right there. Hope you had an informative time, kind of grabbing some information here and kind of reviewing or being reminded of some of these things. I'm going to stop it there, though. So yeah, thank you for watching. If you have any other questions, see your Honors Pre-Cal teacher. Until then, though, have a great rest of your day, night, or even your year. I'll be there for... Is that the Friends theme? I've seen one episode of Friends in my life, and I'm singing the Friends theme song at the end of the video. What is the world coming to?